Hello students, welcome to Sri Chandra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 4 of unit Moving Charges and Magnetism. In today's class we are going to discuss about the applications of the Biot-Savart law. In the previous class we were discussing the magnetic field due to magnetic field due to straight current carrying conductor according to the Biot-Savart law. Let's suppose this is current conductor I, and here it is the point where magnetic field is required. The separation is R. What we are supposed to do is we just make a line at the end point of this wire, make an angle, a second line at this end point of the wire. Let's suppose this is alpha and this is beta. Then we used to have this, that B should be magnetic field should be equals to mu naught I divided by 4 pi r into bracket sine of alpha plus sine of beta, and the direction will be inside the plane. We used to rotate it, we used to have an imaginary circular curve and find out the direction of the magnetic field. I hope you remember this. Yes, so let's practice this more and work for it. Now this is very logical question. Please have a look at this very carefully. Let's suppose that this is a straight line and this is having length 2L. One of the conductor is there, another conductor is here, and due to these two conductors, even this is 2L, even this is 2L. Magnetic field at this point P is required. I hope this is clear. Yes, this is current I1, this is current I2. If this current is flowing in the downward direction, and this current, let's assume that at a first this current is, even it is moving in downward direction. So I hope this is understood clear, that you need to find out magnetic field at point P. Yes, you need to find out a magnetic field at point B. Let me make somehow it is simpler. Yes, that both the currents are same, it will be easy to calculate. So now start doing it. How will you do it? First, understood that this currents are moving in the inside the plane containing this line. Yes, that means it is perpendicular to this plane. So first work for the magnitude of this, and when it says it is inside, that means they want that you need to consider this wires or this current carrying conductor as the infinite current carrying conductors. These are the infinite current carrying conductors. So let's give them a notation. It's a first, this is second. Let's just find out the magnitude. B1 is equals to mu naught I by 4 pi r. R is the 2L multiplied by sine of 90 plus sine of 90, because now we have already discussed in the previous class that if it is the infinite segments, the angle would be a 90 degree. So this is sine 91, sine 91, this is 1 plus 1 2. This is equals to mu naught I by 4 pi multiplied by 2L multiplied by 2. This 2 has gone, and that should be mu naught I by 4 pi L. Now what would be the magnitude? What would be the magnitude of B2? Even it would be the same, because even this is infinite current carrying conductors. So magnitude wise it is same, it's a mu naught I by 4 pi L. Now let's work for the directions. So for direction in this situation you cannot rotate it. You cannot rotate it and make the task done. So at this point you need to use a right hand palm rule. So what the right hand palm rule was saying, it says that use your right hand. So the direction of current will be represented by thumb, and stretch your fingers towards the point where magnetic field is required. So in this situation your palm will represent the direction of magnetic field. So if you do this, let's work for this conductor. First, make your thumb as it is moving inside the plane. Please do this, please use your hand. If you are not going to use this is not going to be done. So please use it, please do it. So your thumb should be moving inside the plane of your book because you have draw this on your book. Yes. Now stretch your right hand fingers towards the point P. Now where do you find your palm? It should be at here in this direction. Now do the same thing. Do the same thing for second segment as well. It should be in this direction. So this is B1, this is B2. As you can see, this is 2L, this is 2L, this is 2L. So this angle must be 60 degree. And if it is 60 degree, this should be 120 degree. Is it clear? Is it clear? So we have a two vectors. They have been aligned with an angle of 120 degree, something like this. This was B2, this was B1. This angle was 120 degree, and B1 and B2 magnitude wise they were mu naught I by 4 pi L. So to find out the B net, look at this. Two vectors are there having same magnitude. So same magnitude would be there. I need to find out B net. This B net should be is equals to 2 into B into cos of theta by 2. That should be equals to 2 multiplied by mu naught I by 4 pi L multiplied by cos 120 by 2, which is a cos 60 degree, and cos 60 is half. So this is 2 multiplied by mu naught I by 4 pi L multiplied by 1 by 2. This 2 has gone, and the remaining term, it's a mu naught I by 4 pi L. Yes, this is the direction of B net. This is B net, mu naught I by 4 pi L. I hope these things are clear. Is it clear? Is it great? Like to do one more question? Yes. This is first conductor, this is second. The length is 12. It is a point P. Yes, this is a point P. Even this would be the 12, and this would be the 12. So what you need to do is that this is current I that is moving inside the plane, and even this is current I that is moving outside the plane. What do you need to do? You need to find out magnetic field at point P. You need to find out magnetic field at point P. So I understand that magnetic field and magnitude would remain the same. So let's do it very quickly, that you understand that this is infinite length current carrying conductors. These are the infinite length current carrying conductors. So do it quickly. Find out the B1 and B2. What is it? It's a mu naught I by 4 pi multiplied by 2L into sin 90 plus sin 90. Now you understand this is 2. So this is equals to mu naught I by 4 pi L. What about the magnitude of magnetic field 2? Is it same? Yes, it's the same. It's a mu naught I by 4 pi l. Now let's work. Let's work for the directions. So for first, use your right hand palm rule. Have your thumb in the direction of the current. It is moving in the downward direction, so your thumb should represent perpendicular to the plane, and it should be within the plane, inside the plane. So B1 should be in this direction. This is B1. Now this would be the B2, because in this situation current is from the outside. Current is from the outside the plane of the paper. This should be the B2. So this is B1, this is B2. This angle should be the B net, and this is 60 degrees. So B net should be is equals to 2 into B into cos of 60 by 2, which is a 30 degree. This is equals to 2 multiplied by mu naught I divided by 4 pi l multiplied by cos 30. That should be root 3 by 2. This has gone, and that should be is equals to root 3 mu naught I by 4 pi l. Yes, this is the direction of B net. I hope this is clear. Is it clear? Any doubts? Any doubts in this? Is there anything? No? Great. Let's work for the next question. Let's suppose this is current I. This is current 2I. This both are the infinite length wires that has been they have extended up to infinite. Yes, and the separation between these two is the 20 centimeter. Let's suppose this is point P. What do you need to do? You need to find out point P such that net magnetic field at point P should be 0. So how could you do this? Take your time. How should you do this so that net magnetic field at point P should be 0? What can you do? What can be done? Yes? Okay, let's have a look. Let's understood that, let's suppose this is point X. So this is separation X. So this must be 20 minus of X. This is X, this is 20 minus X. Consider this as a first segment, consider this as a second segment. So B1 should be is equals to mu naught I divided by, as these are the infinitely extended, this is 2 pi x. Yes, and it is within the plane, it is inside the plane, because if you rotate this, understood, if you rotate this, it is moving in clockwise direction, and clockwise direction represents the magnetic field inside the plane. This is B1. Now what about the B2? It's a mu naught multiplied by 2I, current is there, 2I divided by 2 pi into bracket 20 minus of x. Yes, and this is inside the plane. This is inside the plane because it is moving in anti-clockwise direction. So here B net, that should be equals to 0. That should be B1 minus of B2. This is B net. So that should be is equals to mu naught I divided by 2 pi x should be equals to mu naught multiplied by 2I divided by 2 pi into bracket 20 minus of x. So this 2 pi has gone. This mu naught has gone. This I has been gone. So this is equals to, I have been left with the 2x equals to 20 minus of x. So this is 3x equals to 20, and this x equals to 20 by 3 centimeter. Let me rewrite this. X is equals to 20 by 3 centimeter. So we can consider that this is the null point where net magnetic field will be 0. So from the wire I, it is at 20 by 3 centimeter, and from the wire 2I, it would be a 2 into 20 by 3. I hope this is clear. Is it? Is it clear? Great. So I hope you can do the questions based on this concept. So let's just be ready with your pen and paper. As soon as question is there, you are going to attempt it very quickly, very fast. Let's have a look what question is saying. It says that a wire in the frame of a square of side A carries a current I. Then the magnetic induction, when they ask a magnetic induction, they are indirectly asking for the magnetic field. Yes, please do remember this. At the center of the square wire is, yes. So this is the situation. Side is A and it is carrying current I, something like this. You need to find out magnetic field at this point P. So can you do this? Can you? Are you sure? Or shall I do something for you? This distance should be A by 2. If I make an angle, this should be 45. Even this should be 45. So this B1, it's a mu naught I divide by 4 pi into bracket A by 2 into bracket sine 45 plus sine 45. It's a 1 by root 2 plus 1 by root 2, which should be a 2 by root 2. So this is equals to root 2 times of mu naught I divide by 4 pi into A into 2. It's a 2 root 2. It's a 2 root 2 mu naught I by 4 pi A. But this is of this alone wire. I need to add this for the 4 wires. So B net should be equals to 4 times of B1. This is equals to 4 into 2 root 2 to 2 root 2 mu naught I divide by 4 pi A. Now it's a 2 root 2 mu naught I by pi into A. And as I have shown the direction of current in the clockwise direction, this should be inside the plane. If I have shown it in the anti-clockwise direction, it should be outside the plane. I hope this is clear. Is it clear? Is it? Great. Let's work for the next question. What is it? It says that an electric current passes through a long straight wire. Okay. At a distance of 5 centimeter from the wire, the magnetic field is B. The field at 20 centimeter from the wire. Okay. So if I understood this, that long straight wire, they are asking about the infinite wire. Yes, these are the keywords that people are using. So this B should be is equals to mu naught I divide by 2 pi r. And as it says that certain current is flowing and only the distance is changing, so I can write like this. It's a B directly proportional to the 1 by r, or B inversely proportional to the r. So what I need to do is, it's a B2 divide by B1, this is equals to R1 divide by R2. So B2, that is what I required. B, it is the B itself. R1, it is the 5 centimeter distance. And what I required magnetic field as 20. It's a 5 4s are 20. So B2 is equals to B divided by 4. As soon as distance is increasing, this should be decreasing. So this is B2, that should be is equals to B by 4. Is it clear? Yes, very easy. Let's work for the next question and do it fast. What does it says? A current of 1 ampere is passed through a straight wire of length 2 meter. Okay. The magnetic field at a point in air at a distance of 3 meter from one end of the wire but lying on the axis of the wire. Okay, great. So what you need to do is first have a rough sketch of it. That this is a current carrying conductor that carries a current of 1 ampere, and length of this wire is 2 meter. This must be a 2 meter. Yes, the magnetic field at a point in air at a distance of 3 meter from one end of the wire but lying on the axis of the wire. So you want a magnetic field at this point. This is at point P, and this must be 3 meter from here. So what was your answer? What was your answer? If you remember our concepts in the previous class, it's a second number concept that if you extend your length, and you will find that it is the same point, where magnetic field is required. In this case, theta is equals to 0, so sine theta would be equals to 0 and magnetic field will be 0 straight away. That's it, nothing to do. I hope this is clear. This can be represented like this as well, that this is the current carrying conductor and you want a magnetic field at this point. So this would be the 0. I hope this is clear. Is it clear? Is it? Are you sure? So can you do this kind of questions? Can you? Great. Now let's work for the next question. Do it fast. You are doing great job. Well done. Keep going. Let's have a look. The magnitude of a current in a long straight conductor to produce a flux density, again a new keyword to represent magnetic field. Flux density of 2 microtesla at a distance of 10 centimeter from the conductor is, okay, so B is equals to mu naught I divided by 2 pi r. Yes, what do you want? You want a flux density, that means you want a magnetic field of 2 microtesla, that means 2 into 10 to the power minus of 6 Tesla is required, where at a distance of 10 centimeter. At a distance of 10 centimeter, this is mu naught, which should be 4 pi into 10 to the power minus of 7. Current is required divided by 2 pi multiplied by r, that is of 10 centimeter. So centimeter needs to be converted, so 10 divided by 100 and divide, that has gone there. It's a 2 this 2 has gone, so I'm left with this is 10, this is 100, so this would be the 10. This is equals to 10 to the power minus of 6 is equals to this is even 10 to the power minus of 6 multiplied by, because here it is minus 7, here it is 10 to the power 1 multiplied by I, and I could be written as 1 ampere. That's it. Yes, these are very easy questions. Yes, questions of approximately 20-30 odd seconds and not more than that. Is it clear? Is it? So will you be able to perform this? Are you sure? Are you? Can you do this? Great. Let's work for the next question. What does it say? That A and B are the sections of two long parallel wires placed perpendicular to the plane of the paper. Okay, great. They are again perpendicular to the plane of the paper. Let us suppose assume that this is conductor 1, this is conductor 2, A and B. They carry current of 5 ampere and 10 ampere respectively. This is of 5, this is of 10, in the directions indicated in the figure. Okay, they are inside the plane. If the separation between them is 3 meter, the zero of the magnetic field in the plane of the paper is at a point of yes. So one of them should be outside the plane of the paper. Then and then you can have a zero magnetic field. Yes, great. So how should I do this? First find out, let's assume that this is X, where magnetic field is 0. If it is X, this must be 3 minus X. So at point A, at point A, B1 could be written as mu naught I divided by 2 pi x. This is equals to mu naught multiplied by current, a current of 5 ampere divided by 2 pi x. Yes, and if from the wire A current is moving in this direction, use right hand palm rule. Arrange your thumb such that current is flowing. That means thumb is moving inside the plane of the paper, and stretch your finger towards point P. If it is the case, you will find that magnetic field at this point would be in this direction. It's a B1. Now arrange your finger or arrange your thumb in the direction of the B1. Arrange your thumb in the direction of B1. So again, I made a mistake. It must be in the downward direction. It must be in the downward direction. Sorry. Yes. Now arrange your thumb in such a way that it is moving inside the plane. So this is B1 and this must be the B2, and this 2 should be same in magnitude. Then and then they can perform a zero magnetic field at that point. So this B2 could be written as mu naught multiplied by current. It's a 10 ampere divided by 2 pi into bracket 3 minus of x. So let's just compare the B1 and B2, because I want that B net should be equals to B1 minus of B2, and that should be equals to 0. So this is mu naught multiplied by 5 divided by 2 pi x. That should be equals to mu naught into 10 divided by 2 pi into bracket 3 minus of x. So it's mu naught has gone. This 2 pi has gone. That's a 5 2s are 10, and the situation is 2x is equals to, this is 2x is equals to 3 minus of x. So this is equals to 3x is equals to 3, and x is equals to 1 meter. Yes, x is equals to 1 meter. So if it's an x equals to 1 meter, if it is at 1 meter, then it must be a 2 meter from the segment B, and this should be the answer, 2 meter to the left of B. I hope this is clear. This is clear. Is it? Is it clear? Are you sure? Can you do this? Are you? Great. Now let's work for this question. Very logical question. Very logical, and one of the favorite question of the examiners when they are preparing a paper for the medical aspirants. Yes, because this has been asked twice in medical examination and only one time in the JEE examination. So what does it say? Look at this very carefully and go with the data, and let's just find it out. It says two long straight conductors with currents I1 and I2 are along the x and y axis. Okay, great. Then the equation of locus of points of zero magnetic induction, again new word, a magnetic induction. Even this will represent a magnetic field. So take your time of 30 seconds and let me know what we should do. How will you do it? How will you do it? Do you find any solution to this? Do you? No? So shall I do it for you? Shall I? Okay. Have a look at this. Let's suppose, always assume that when two conductors are there, which have been placed perpendicular to each other, then a zero locus will be always there on the diagonal of them. This could be one of the probability. I am not telling that this is the answer, but this could be one of the probability, and this could be the other probability. But other than this, there is no possibility of a zero locus. I hope this is clear. Yes, is it clear what I am saying? That when two conductors are there which have been placed perpendicular to each other, then to find out a zero locus, you must understand that the zero locus could be there on one of the two diagonals. Other than this, there is no possibility of zero locus. Yes, I hope this is clear. Now, what you need to do is assume a random point. Let's suppose this is point P, and find out the magnetic field due to both. So, it is something like this, that this is I2, this is I1, and you want a magnetic field at here. So first, only you need to focus only on the directions. So now use the right hand palm rule, or use the, even you can make a circle, and just try to find it out, that what would be the direction of magnetic field 1 and magnetic field 2. This is magnetic field 1, this is magnetic field due to 2. So if you rotate this, this is moving in the anticlockwise direction, so this B2 would be outside the plane of the paper. If even if you make this as a circle, even this is moving in the anticlockwise direction, so even this is on the outside the plane of the paper. As two vectors are in the same direction, they are not just going to subtract it, they are going to add this, and when they are going to add this, they cannot form this. B net could not be equals to 0. I hope this thing is clear. So this possibility, this could not be zero magnetic field. So this possibility has been over. Now let's work for the first possibility. So the situation is that this was I1, this was I2, and we were working for this. Let's randomly choose a point P. Now find it out the magnetic field due to first. So if I make a certain loop over here, something like this, this is the clockwise direction, and as it is a clockwise direction, B1 should be inside the plane. Let's work for this, something like this. Yes, and this is in anti-clockwise direction, and as it is in anti-clockwise direction, it is outside the plane. So as one of the vector is inside the plane, one of the vector is outside the plane, this could be the probability where net magnetic field will be 0. So this could be the case for sure, and this can be done. So now if this can be done, what I understood is that, let's just check it out, that this is the X, this is the Y. So my B1, let's suppose this is the point where this distance would be the X. So B1 could be mu naught I1 upon 2 pi x1. Same way, this is the point where this location is Y. So from this wire, this is a distance Y. This B2 should be is equals to mu naught I2 divided by 2 pi into Y1. As B net should be equals to 0, and if it is 0, this is b1 minus b2 should be equals to 0. This is equals to mu naught of I1 divided by 2 pi into x1, that should be is equals to mu naught of I2 divided by 2 pi into y1. First thing, this mu naught has gone, this 2 pi has gone, so it's I1 y1 is equals to I2 x2, and arrange this according to the options given. But do you clear with this, that when two current carrying conductors are given, and when they want that net magnetic field will be a 0, always go for two diagonals only, because it is only the two possibilities, because there are only two possibilities is possible where net magnetic field could be 0. I hope this is clear. Is it clear? Is it? Okay. So I'm giving one question for you people, that you are going to attempt this on your own. That let's suppose in the previous question, find out locus of points having zero magnetic field for given figure. This is x, this is y, and here the current is moving in this direction. This is I2, this is I1. You need to find out the locus and you need to derive a relation. I hope you will do it. Yes, so this is, try yourself. You are about to do this. Yes, and I am sure you will able to do it. So let's move to the next question very quickly. Let's have a look. What does it says? Do it quickly. A straight wire of length L carries a current I amperes. A point P, yes, at this point, when joined with the ends of the wire, forms an equilateral triangle. Okay, it's an equilateral triangle. The magnetic induction at point P will be, okay, so what I understand is this is 60, this is 60, this two together is a 60. So this would be the 30 degree and this would be the 30 degree. Yes, this length, is it clear? Yes. So this length, half of the length will be treated as an L by 2. Even this half will be treated as an L by 2. Now from here to here, the distance from here to here, the distance could be calculated as, let's suppose this is R, that 1030 degree, it's an L by 2 divided by R. So this R is equals to L by 2 multiplied by 1030 degree. This 1030 is equals to L by 2 by R. Yes, yes, it 1030 degree, this is the 90 degree. Yes, this is 1030 degree, it's an L by 2 by R. 1030 is equals to L by 2 by R. Yes, so R is equals to L by 2 into 1 by 1030 degree. So this is equals to L by 2 into 1030, it's a 1 by root 3. So this is equals to root of 3L by 2. Now we have a distance. Now let's just work for the magnitude. This is the current that has been flowing. It is flowing in the clockwise direction, so magnetic field will be inside the plane. So this is the situation. This is current I, this is point P, this is location R. Yes, and if I make to connect this, this is 90 degree, this is 60 degree, 90 plus 60 150, this must be the 30, this must be the 30. So this B1 should be is equals to mu naught I divided by 4 pi r. I'm going to replace this r at the later part into bracket sine 30 plus sine 30, that is of 2 into sine of 30 degree. So this is equals to mu naught I divided by 4 pi r into bracket 2 into sine 30, it's in half, this has been gone. So this is equals to mu naught I by 4 pi r. I hope this is clear. Is it clear? Great. Now this is the mu naught I by 4 pi r, but this is for one segment only. So B net should be equals to 3 times of B1. Yes, current is flowing in the same fashion, that means in the clockwise fashion. And when current is flowing in the clockwise fashion, this magnetic field due to all three segments will be inside the plane. And when it is inside the plane, it is going to add it up. So this is 3 times of B1, 3 times of mu naught I divided by 4 pi r. Now we have a value of an r, which should be root of 3 by 2 into L. So let's just have this value. It's a B net, that should be equals to 3 into mu naught I divided by 4 pi multiplied by r. R is the root 3 by 2 into L. So this is 3 2s are 6, or this root 3. So this is root 3, this is 2, this is 2 into mu naught I divided by 2 pi L. This is B net. Got it? Yes, this is B net, which should be is equals to root 3 times of mu naught I by 2 pi L. I hope this is clear. Is it clear? Is it? Are you sure? Great. Let's work for the next question. Yes, it is the same and repeated question. You are going to do this. What does it say? It says a square wire of each of side L carries a current I. Okay, this is current I. The magnetic field at the midpoint of the square is, yes, you are going to do this. Yes, this length is given, that is of L, and even the current flowing is I is given. So this is try yourself. We have already did it in the previous class. Yes, so now I'm sure you are going to do this, and that can be done easily. Let's work for the next question. Yes, this is very logical. A very good question. It is the solved question. It is the solved question of NCRT. Yes, so please understand, the level of NCRT is very good, and you must go for it. Yes, let's have a look. What does it says? A two wire AO and OC carrying currents I as shown in the figure. One end of the both the wires extends to infinity. That means this end has been extended up to infinite. Even this end has been extended up to infinite. And angle AOC is alpha. Okay, the magnitude of magnetic field at a point P on the bisector. Okay, great. So this should be the alpha by 2. Even this should be the alpha by 2. At a point P on the bisector of the two wires at a distance r from the O is. So now what you need to do is that this wire having one of the side as an infinite, and when one of the side is infinite, so what you need to do is, let's just assume that this is the perpendicular distance, and on this side the angle would be 90. On one of the side the angle would be the 90. So, and as this is the point where it is going to be infinite, so this is 90 I'm talking about. This would be this would be the 90. So the another angle would be equals to 90 minus alpha by 2. So your alpha, let's assume it's a 90 degree, your beta should be equals to 90 minus alpha by 2. I hope this is clear, first part. Now the second part, what would be the direction of magnetic field due to both the wire? As you can see, thus that current is flowing in the same manner. So magnetic field due to first wire, let's understood this as a first and this as a second. So B1 would be inside the plane, B2 would be inside the plane. So what you need to do is you need to just calculate it. You need to just calculate this according to the any one of the wire I'm going to derive, and just I need to multiply it with 2. So let's just have a look. So the situation is magnetic field at point P, that should be is equals to mu naught I by 4 pi x. This is equals to mu naught I by 4 pi x into bracket sine of 90 minus alpha by 2 plus sine 90, while x can be written as this perpendicular distance. This perpendicular distance is r sine alpha by 2, because this angle is bisector and this is alpha by 2. So let's just replace the value. It is the mu naught I by, and this has been multiplied by 2. Here it is. So it's a mu naught I by 2 pi r into bracket sine of alpha by 2. Replace the value of x into bracket sine 90 is 1, and sine 90 minus theta, it's a cos theta. So here it's a sine 90 minus alpha by 2, it's a cos alpha by 2. So let's just try to get it done. It's a mu naught I by 4 pi 2 pi r into bracket 1 plus cos alpha by 2 into this is sine alpha by 2. I hope this is clear. Yes, this is replaced, this is divided by 1. So this is mu naught I by 2 pi r into bracket 1 plus cos alpha by 2 divided by sine of alpha by 2. I hope you got the correct answer. Is it? Is it? Yes. So let's work for the next question. Please have patience. We are on the verge of completion of this session. Yes, so please do this very carefully. Yes. What does it say? It says a current is flowing in a hexagonal coil of side A, each side having a dimensions of A, something like this. Yes, the magnetic induction at the center of the coil will be. So how will you do this? It's an hexagon. And how you are supposed to do is, a current is flowing in this direction and it is leaving from here. So this is the case where B net could not be a 0. Yes, so please don't understood that no, this is the 0 kind of task. No, this is not 0, not at all, because the current entering and current leaving is not making an angle theta is equals to 0 at which magnetic field is required. So this is not 0. Start working for it. One more thing, for every magnetic field they are moving in the clockwise fashion, and as they are moving in the clockwise fashion, this B net could be written as 6 into B. I hope this is clear. Now let's assume any one of the side, something like this. Then this would be the distance, and this angle and this angle, this both would be the 30 degree. Do you understand this? Do you understand this? Great. So this would be the 30 degree. This is point P. So let's just calculate for any one of the side, and then I will multiply it by the 6. It's a mu naught I by 4 pi r multiplied by sine theta 1 plus sine theta 2, and this theta 1 and theta 2 equals to 30, and now you can easily calculate this y as well. So this is y. Yes, according to the trigonometry, this could be written as y is equals to root 3 by 2 into a, and thus B net could be have, it's a root 3 times of mu naught I divided by pi into a. Is it clear? Is it clear? Great. So let's just wind it up this session over here. This is the all questions. These are the questions that were using the applications of the Biot-Savart law for the straight wire. This is only for the straight wire. In the next session, we are going to discuss about the magnetic field due to charged arc according to the Biot-Savart law, and we are going to practice the question based on this. So your one of the application of the Biot-Savart law has been completed. Now you can do all the questions. Now you can do all the questions that are based on the magnetic field induction using the Biot-Savart's application. So please, it's a humble request that do as many questions as possible. You need to perform at least approx 100th or 150 questions for this single application, because what I want that doing so much of practice will make this concept very clear, and this is the concept where you are not going to revise it, even though it will be with you. That means you will remember it very easily. Once you have practice over it, once you have command over it, it will be for yours forever. Yes, so please do this. This is the requirement. Thank you. Have a good day. Take care. Bye bye.